level so that you know what are the resources you're going to need. You can see the area of the plume so that you know what route shouldn't be used for evacuation, and you can understand, is this a localized problem where I need to evacuate 50 people, or are there 10,000 people that are downwind from this and I need to take larger scale action? So these are the type of tools that we try to provide. And what we do is we're happy to provide an answer that's 80 or 85% accurate instead of 99% accurate if we can give you an answer within the time constraint you give us, right? If you say you need an answer within 3 seconds, you need to know what that sign in a foreign character set says, and you need it spoken into your ear, then we'll do that, and we may be 80% accurate. If we're running offline for 5 minutes, we might be able to give you 99% accuracy, but 3 minutes later or 5 minutes later, that answer might not do you any good. So we're willing to take that engineering solution and let you know the reliability of the information that we're providing you. So those are some of the type of things we do from sort of the hazardous material and emergency evacuation. We provide more command center tools with some of the work that's been done from the GeoVista Center, looking at sense place for infectious disease modeling, looking at new ways to analyze Twitter feed data with sense place 2, so that you can actually see a history view, searching for information, see the 500 most relevant tweets, having spatial filtering capability, being able to rank those tweets for their relevance, looking at time filtering capability, providing this all into a real-time display system to allow you to localize your inspection for a given area. You can do similar things when you actually try to then go and look at multiple ways to put this information together in a large-scale decision-making process where you have hypotheses and you can integrate the data into different chains of reasoning, and you can start looking at anomaly detection. We've recently been looking at trying to pull out statistical patterns for anomalies so that you can have the predicted data that you expect. You can then find when it's an anomaly. If an event would happen on the Purdue campus on Friday night and there was a shooting, which happens once every few years, luckily, there may be 10 or 20 tweets about that, or there may be 500 tweets about partying. Most people use frequency of tweets and won't find that, but if you have the statistical model, we do anomaly detection first. And so you can actually see that here, where this is looking at the remainder from the expected signal, so that earthquake immediately pops up in looking at this in the Baltimore, Washington area. You can also look at correlation among multiple social media. So when you look at Flickr, Twitter, YouTube, and other sources of data, you can generate your z-values to understand whether you have significant aberrations from them. Can we start to correlate and integrate these several signals, understand the time delay that it takes before something shows up on YouTube versus Twitter, and start correlating these together and build up models to understand the temporal interaction of these multiple sources of data. So we try to bring in multiple sources of data to help people understand things. And the final example that I'll go over is looking at our public safety coalition in Indiana and Ohio, where we're working with law enforcement, helping them to try to understand and do their job better. We have it where we have both desktop and mobile-based versions of the system. This looks very similar to the type of display we developed for the Coast Guard. This was developed first. We created the display for the search and rescue question for the Coast Guard within 2 weeks. From the comment of just Admiral Parks wants to know what's going to happen with the Coast Guard Auxiliary retiring. Could you adapt that to it? And it's like, well, sure we could. So we've been working very closely. We have the predictive capability to give you the window into the future of what we expect to see there. We can allow you to look at certain things. We're looking at high incident, high risk alcohol behavior in the Purdue campus, part of a network of 100 schools that got a grant in the US to evaluate this. And so you can start looking at the campus. This is results I'm just reviewing for a presentation my student's giving tomorrow to the group. And you can try to say, what is the temporal distribution? Not surprisingly, 3 a.m., 2 a.m. is the most popular time for the drunkenness public intoxication data. You can look at the day-a-week effect. Of course, it's not surprising that it's occurring on Fridays, Saturdays, Saturdays and Sundays. Sort of the surprising thing is looking at certain weeks and seeing Tuesday as a spike, and it's because when students come back to campuses, bars will run promotions because they don't tend to get them in during the week, and they have special drink deals, is what we found out. You can look at the relationship of our students tend to drink more in terms of football games as opposed to hockey games, but you can look at the peaks compared to when the football games occurred, whether they're home games or away games. You can try to say, was it a win or a loss? Purdue Notre Dame had a spike. Homecoming had one of the biggest spikes, but actually the biggest one was contested game of Purdue versus Iowa, where they lost. So it doesn't seem to matter whether you win or lose. There's a lot of alcohol behavior going on. We can look at things in terms of violations in dorms for underage drinking. We can look at emergency run data to see how many of these people were actually taken to the hospital but not cited. We can look at driving while intoxicated issues for all of this. So we've then started to try to say, can we correlate this data and look at multiple signals? And if you look at a large-scale amount of data, oftentimes you miss the distribution and signals within the data. So if you look at relationship between drug abuse and burglaries, you find that there isn't a strong correlation across the entire area because there's spatial locality to these patterns, which I guess is good. It turns out that you're not likely to have a burglary of your residence in our area from people who are drug offenders if you don't live in a drug-infested area. So it's sort of, if you look at the correlation of the given neighborhoods where there's high drug incidents and burglaries, you find that there's zero lag for maximum correlation of these effects. If you actually look at trying to correlate drunkenness and traffic incidents, you find that within -4 to +5 hours, there's a strong correlation of both occurring simultaneously. Then you see a peak in correlation again in the day before and the day after, which you find is an indication of the amount of traffic and people coming to our community, because a lot of these incidences actually occur on football weekends. So high incidence of drinking violations on Friday night tends to lead to a lot of accidents on Saturdays. So it just is there are two signals coming from, there are two artifacts coming from an underlying distribution that aren't causally related, but they're indicative of allowing you to predict for the future. And I was just going to show you one last example here of this running. And if you go through and play, I just selected here looking at drunkenness and liquor law violations, you see that the campus area is predominantly where it all occurs until you get to the summer, and then it moves over to the rest of our community. Because when students are gone, so it's the highest thing that you can see. But you can choose all your different hierarchies here for the law enforcement based on the public classification, or you can go into the underlying UCR code classification. And we're looking at a lot of different things for them there, but that just gives you an idea. We have spent a lot of time with our end users of how do we transfer this information onto mobile devices. And so we have iValet, which I was going to demo on my iPhone, but my license expired, and I need to get connected before being able to demo it, but we can show it on the iPhone, the iPad, looking at different ways to allow you to use time and space information so you see things closer to your time. If you're responding to a call, you're going to knock on a door, what do you need to know? You need to know what's happened recently around this location, what type of events have occurred during this time period. So we changed the displays to allow you to see those type of things. Our partners at Penn State have worked very closely with the Harrisburg Police Department, creating web-based tools for them to understand crime patterns as well, and we've integrated some of the statistical models back and forth for this. When we look at the crime data, what we keep on getting, as with most types of situations, more and more data that people want to integrate together. Looking at weather and phase of moon data, looking at streetlight locations, looking at bus routes, looking at civil court data, looking at social media data. How do we integrate all this together to make sure that it's a better model that we're providing to them? And what we really focus on is what helps the officers, detectives, or police chief, who all have different types of jobs, do their jobs most effectively. Just briefly, I'll say we also do things if you have large-scale collections of documents in multiple ways of linking together the people, places, and events with a project called Jigsaw. We also have a project called Seesaw that, again, tries to help people understand the analytical reasoning for this. We do work with mobile phone-based gang graffiti recognition. We've got over 60 officers in Indiana currently using this and over 600 different images that have been uploaded into the database. And I thought we could provide a spelling tool for the gang members so they learned how to spell, but that's actually how the Goon Squad, the name of the gang, spells their name. They misspell it. So it just shows you. But there's a lot of information that's useful in providing spatial temporal analysis and real-time image analysis of this information. And if we look for the future, I'll briefly give you 6 challenges in trying to integrate and advance visual analytics. And first is, how do we create the environment that balances the human and the computer most effectively and integrate it into a seamless way of presenting data? How do we get appropriate simulations and analytics in there and make them understandable to the end user so that they know what they can trust and how to interpret those? Can we deal with problem scales increasing dramatically and allow people to look at cross-scale problems? Can we allow them to reason more effectively about time and uncertainty, which humans seem to have trouble in doing? Can we allow them to make effective risk-based decisions? And can we develop the correct way that people should interact in these environments? And so just an example of real-world scale, if we really are trying to take in the over 100 real-time video feeds from the new Meadowlands Stadium in New Jersey coming in to do real-time video analytics, can we scale it up so that it works? Currently, they can do anomaly detection when the stadium's empty, but they don't have video analysis algorithms that run at that scale. But can we use a platform such as Longhorn that the National Science Foundation funded that has 512 GPUs, 2,000 CPU cores set up for interactive analysis and visualization? So those are the type of resources that we assume every police station will have in 10 or 15 years. Although maybe it's 20 years with the rate of the economy in the US. But then, the final thing I'll just briefly mention is the science of interaction, is how do humans create knowledge through the manipulation of an interface. We're coming out with something for this where we're trying to define what are the challenges and what are the benefits of doing this, dealing with things such as fluid interaction and having a visual discourse